Heracles, Heritage Resilience Against Climate Events on Site, Training Course Number 10. For many years now, information and communication technologies have been offering an ever-increasing support to cultural heritage, preservation, and exploitation. Course number 10 illustrates the Heracles platform as a tool for the stakeholders and end users dealing with the maintenance and restoration actions of cultural heritage sites against the effects of climate change. This course is organized into 5 chapters: operational context, domain model, platform architecture, platform deployment, platform unique features. Operational context. The central aim of the Heracles project is to design, validate, and promote responsive system solutions for effective resilience of cultural heritage against climate change effects, considering a holistic, multidisciplinary approach through the involvement of different expertise: end users, industry SMEs, scientists, conservators, restorators, and social experts, decision and policymakers. This is operationally pursued with the development of an ICT platform able to integrate heterogeneous data from multiple sources, analyzing the data to evaluate the state of the CH assets and related risks, integrating predictive models, and supporting decision makers to plan short and long-term maintenance and restoration actions in order to effectively provide complete situational awareness and support decision for innovative measurements, improving CH resilience. The effectiveness in the integration capacity of the Heracles concept and platform is validated in 4 different test sites: Knossos Palace and Koules Venetian Fortress, located in Heraklion, the medieval walls and Consoli Palace, located in Gubbio. This slide illustrates the operational context diagram. The main users of the Heracles platform belong to 3 groups: decision makers, represented by the site manager in the diagram, domain experts, and on-field users. While domain experts and decision makers access the platform through the integrated dashboard from connected desktop computers, the on-field users can access through mobile devices such as tablets and smartphones. The site manager relies on the consultation of domain experts whenever domain-specific analysis are required. Models, as well as in situ and ex situ analysis, are run outside the platform by the domain experts, but the platform provides the functionalities to store and retrieve the results of these analyses. The heterogeneous data stored in the platform provide the basis for risk assessment. Moreover, the platform provides full real-time alerting functionality and workflow management support when a threat is identified. While the integrated dashboard provides the full range of situation awareness and decision support functionalities implemented within the platform, the mobile application is limited only to the alerting functionality that enables a user on the field to send and receive alerting messages. This slide illustrates a simplified workflow that can be applied to a generic cultural heritage management scenario. First step is data collection. This includes all measurements and derived parameters for 3D and shape reconstruction, geomorphological and cinematic modeling, and structural measurements to evaluate the state of cultural heritage assets, as well as the parameters, which may have an impact on their conservation, such as weather conditions, humidity, ground movements, etc. The second step regards high-level monitoring. This takes into account measurements and models that cover both the CH assets and their surroundings. At this level, satellite images, meteorological data, and geographical models, among others, are used to diagnose problems and determine possible threats. A third step involves local monitoring. This refers to in situ measurements and models directly related mostly to the CH assets, such as measurements performed by sensors, structural models, and physical-chemical status of the materials. The risk analysis algorithms will use the data produced by the sensors to estimate the risk levels at a given site. The fourth step is involved with selection of countermeasures and mitigation actions. When a threat is detected, the platform will guide the operator to choose the best workflows containing countermeasure actions prepared by a domain specialist. The workflows include steps to be carried out to manage the situation and the stakeholders that need to be involved and contacted. The fifth step regards the execution of the countermeasures, which may require bureaucratic processes according to specific domestic legislation. It is not controlled by the platform. Nevertheless, interventions can be documented in the system together with planned actions in order to determine their effectiveness. A sixth step involves assessment of the performed countermeasures and mitigation actions. These can be assessed through the data collection and monitoring procedures of steps 1, 2, 3. What are the requirements for the platform? First of all, to read and store online data coming from in situ sensors and connected devices or services, and provide the means to import required data obtained through measurement campaigns, lab tests, and data analyses performed offline. Another requirement is to use historical and current data to assess current site status and threats. Then, to enable interactive visualization of the collected data and the derived results produced by processing other algorithms and models. A fourth requirement is to provide different granularity levels of visualization covering global and detailed views. Still, another requirement is to be accessible from connected desktop computers and mobile devices such as tablets and smartphones. Finally, another requirement is to support the definition of user profiles with different access rights and visualization options. The system will feature at least a user profile for organizations taking care of daily operations and an expert profile for experts that need a deeper understanding of the information managed by the platform. Still, other requirements are to generate alerts to inform about detected threats and anomalous behaviors, which can be anything between immediate and long term. Then to display generated alerts on the platform's UI and send notifications via email, SMS, or other communication technologies. Another requirement is to take advantage of predictive models to enable preventive actions. Still, another requirement is to display countermeasure workflows to respond to the detected threats. And finally, to support the execution of standard operational procedures associated to risk and damage assessment, prevention, mitigation, remediation, and restoration. This slide describes the different classes of sensors used in the Heracles project and the different types of data these sensors produce. The sensor types can be online, offline, remote, in situ, ex situ, machine interpretable data, non-machine interpretable data. The sensor data types can be time series, geospatial coverages, geospatial shapes, other documents. Regarding online-offline, the online sensors perform measurements and transmit the readings to the system without human intervention. Offline sensors require human intervention before the readings become available to the system. Regarding remote in situ, ex situ sensors, remote sensors observe the subject from a distance, while in situ and ex situ sensors need to be located at the same location as the observed subject. In the case of in situ measurements, the sensor can be brought to the subject. In the case of ex situ measurements, the subject or a sample of the subject has to be brought to the sensor. Machine interpretable data, non-machine interpretable data. Machine interpretable data can be processed by the system without human intervention. Non-machine interpretable data requires a human to interpret the data. Regarding sensor data types, the main types of data relevant for the Heracles project are time series. The time series are measurements of the same observed property, for instance at the same temperature, taken at a more or less regular interval, for instance every hour. They can be taken by a sensor with either a fixed location or by a moving sensor. Fixed point time series are generated by, for instance, the meteorological stations, which will be installed on several sites, or the LVTT sensors that measure the relative displacement of 2 points across a crack. These sensors are located in situ and generate data at a fixed time interval. Moving point time series are generated by the payload monitoring system that measures several atmospheric parameters. These sensors can be handheld or mounted on a vehicle or drone and have a different location for each measurement. Both types of time series are typically stored in servers that implement the OGC Sensor Observation Service Standard, or the OGC Sensor Things API Standard. The Heracles platform uses the OGC Sensor Things API to manage time series data. We also have sensor data types, which are geospatial coverages. These are typically generated by satellite, aircraft, or drone-based sensors, or by mathematical models for spatial interpolation. They are images where each pixel represents a measured or processed value of an observed property for a certain geographical region. Depending on the exact sensor type, a pixel can represent a region of a few square meters up to many square kilometers. Typically, geospatial coverage data is stored in a web map service or a web coverage service like a geoserver. Then we have another sensor data type, which are geospatial shapes. Geospatial shapes are 2 three-dimensional drawings of things like buildings, geological features, borders, or points of interest. This type of data is typically stored in shapefiles or served using an OGC web feature service. Finally, there are other documents. This class covers all the non-machine interpretable data types. Examples are photos, results of chemical analyses or microscopy, and the raw and processed data from a GPR measurement campaign. The Heracles platform will not be able to automatically interpret these data and can only store the files as they are. It can present their availability at relative points in the platform depending on the available metadata. For instance, if the geolocation of the measurement is available, the platform can show the availability of the data as icons on a map. Or if the data is part of a measurement campaign, it can list the files together with the campaign. If the data consists of image files, the platform can display the image, but the interpretation of the image has to be done by an end user. In the Heracles platform, not all combinations of the above classifications are present. So far, the following 4 classifications of sensors have been identified to be most relevant for the Heracles platform. These are online, in situ, and machine interpretable. We're talking about temperature, LVDT, etc. The offline, in situ, machine interpretable, and here we're talking about wave gauge data, etc. The offline, remote, machine interpretable, and here we're talking about satellite, drone-based sensors, etc. And the offline, in and ex situ, non-machine interpretable data. And here we're talking about photos, observation notes, material spectroscopy. Besides these actual sensors, mathematical models can also be seen as virtual sensors. Depending on the way the models are integrated into the Heracles platform, they can be classified as offline or online. This slide contains a non-exhaustive list of identified models for use in the Heracles platform. They are divided into subclasses. First of all, we have geomorphological modeling models, and these contain geomorphological monitoring models and hydrodynamic modeling models. The second class is the structural analysis and monitoring models. This class contains deformation monitoring models, structural monitoring by multivariate statistical techniques, structural monitoring by means of inverse velocity techniques, finite element modeling models. Another class is climate and weather models. Here we have weather research and forecasting models, micro-swift models, microclimate monitoring and analysis, microclimate modeling models, and the CGCM Model E2 plus WRF ARW models. Finally, we have the anthropogenic pressure modeling. This class contains CHIMERE and FARM models and PMSS models. Computational models are used to evaluate the health status of the assets, detect problems, make predictions, and evaluate the risk associated to the assets. Due to their complexity, models are not directly integrated into the Heracles platform. Instead, they are ran offline by domain experts, and their outputs are imported into the platform for a subsequent processing and integration with other data. The data models are integrated using OGC standards like Web Map Service, Web Feature Service, and Web Coverage Service, as well as Web Processing Service. This last slide deals with model activation. The models used by the Heracles ICT platform operate in different ways. Some of these models are continuously in operation and produce updated results on a regular basis, or when new input data, for instance sensor measurements, are ingested into the models. Other models require explicit activation in order to be run and produce results. The preferred way to interact with the models is through web APIs. In general, web APIs are the interfaces through which interactions occur between an enterprise and applications that use its assets. When used in the context of web development, an API is typically defined as a set of hypertext transfer protocol request messages, along with a definition of the structure of response messages. Usually this protocol adopts an extensible markup language or JavaScript object notation format. Based on the discussion with the model owners and managers operating the Heracles project, it has been pointed out that it is not always possible to programmatically interact with the models through APIs. Therefore, alternate ways to enable their utilization are required. In order to perform on-request activation of the models, two ways have been identified. Synchronous activation. The client, in other words, the Heracles platform, makes a request through an API offered by the model owner. The model is run, and when the request completes, the results are available. Asynchronous activation. The client, Heracles platform or end user, makes a request to an interface made available by the model owner. Such a communication may be activated through a web API or email. Further interactions may be necessary with the client in order to gain the detailed information for a proper definition of the configuration of the model. The model runs, and upon completion, the client gets informed that the results are available. The notification of the availability of the results may also occur in different ways. For instance, the model owner sends an email to the user that requested the model results, or if the model offers an API, a client application can use it to check if the model completed its execution. Then we have the access to model results. A number of alternatives are also considered in relation to how the computer results are made available to the client. The preferred modes for a model owner to publish the results generated by a model are manual upload. The model owner uploads the results to the Heracles platform using an online form. Or automatic upload. The results generated by the model are automatically ingested into a data store that provides an API to programmatically access the data. The second chapter is domain model. Heracles ontology. The central information model of the Heracles ICT platform is represented inside the knowledge base as an ontology. Ontologies contain complex and formal collection of terms. These vocabularies have precise and logical descriptions of the relationship between elements of a specific domain and their properties. The ontology itself has a generic description of its domain, but no objects in particular. Before an actual instance of an object is created, concrete values for properties are set to 0. Ontologies are being used to explore and define the entities, also called concepts, and relationships that need to be represented in the knowledge base of the Heracles ICT platform. Ontologies are used to implement the knowledge base of the system, thus enabling semantic queries to facilitate situational analysis and decision-making processes. The design process of the Heracles ontology has included the research and analysis of existing ontologies, but our main concern when extending such in-depth models with missing concepts such as weather phenomena, risk analysis, and crisis management elements was that the resulting model would be overly complex and non-intuitive. Thus, the approach followed in Heracles has been to create a new model from scratch, trying to keep it as concise as possible, while incorporating elements from all the areas that are relevant for the application. RDF is a data model for objects and relations between them and provides a simple semantics for this data model. OWL adds more vocabulary for describing properties and classes, special relations between classes, cardinality, equality, characteristics of properties, and enumerated classes. OWL and RDF were designed to be part of the stack of W3C recommendations related to the semantic web. In the following sections, graphical notation is used to support the description of the Heracles ontology. CH assets. The graphical elements are used in the diagrams are interpreted as follows. Rounded boxes are used to represent the concepts. Directed arrows represent relationships between concepts. A label next to an arrow indicates what kind of relationship exists between the connected concepts. Dashed arrows are used to link subclass concepts to a parent. Dotted arrows are used to link instances to the class they belong to. Fill colors have no specific meaning besides grouping together closely related concepts. The central elements in the ontology are the CH assets that need to be protected against effects produced by climate change. As shown in this figure, a top-level class is defined to refer to any kind of cultural heritage. Assets, which are the focus of the project, are a subclass of CH. The asset concept can be further refined with concepts such as structure and below that monument, building, or wall. Finally, at the bottom, actual instances, the test beds of the Heracles project, like Knossos Palace, Palazzo dei Consoli, Venetian fortification, and Gubbio town walls, can be found. Assets are located in sites, which in their turn can be classified into more specialized classes like cemetery, settlement, and place of worship. Two additional instances, towns in this case, can be found at the bottom left part of the diagram. Heraclion and Gubbio, which are the locations of the project's testbeds. Once the CH assets have been defined, the next step is the identification of the stakeholders that play a role in their management and conservation. As seen in the figure, the stakeholders may be either persons or organizations. In the case of organizations, they may belong to the public sector, the private sector, or to the civil society. These classifications can be further refined with more specific classes, such as the construction sector or research and education institutions. The diagram also includes some example instances of stakeholders. The figure highlights two different subclasses of stakeholders which correspond to the actual users of the Heracles ICT platform, decision makers and domain experts. Decision makers will benefit from the situation awareness and decision support capabilities provided by the platform. Domain experts such as university researchers and professional figures, have the know-how to analyze the more specialized technical scientific information provided by the system in order to provide information in support of those decision makers. Climate and weather effects. The Heracles project aims at preventing the negative impact of climate and weather effects on CH assets. Therefore, aspects related to climate and weather need to be represented in the knowledge base. Additional non-climate related effects, such as bird droppings, can also be represented in the ontology. First, a number of parameters that characterize certain events are identified, for instance, temperature, humidity, precipitation, etc. The evolution of these parameters will cause certain effects to take place, for instance, a heat wave or heavy precipitation, which in turn can lead to additional effects like desertification or landslides. These undesired effects may cause damage to the CH assets. In the figure, an actual example emphasizing the distinction between effect damage type and actual effect damage occurrences is provided. An actual heavy rain episode is a specific occurrence of the generic heavy rain effect type. The heavy rain episode may lead to a fast landslide of a certain magnitude in a particular area, which is an occurrence of a landslide effect type. Finally, the collapse of a part of the wall produced by the landslide is an occurrence of the structural damage generic damage type. Risk management. The main classes related to risk management are displayed in the figure. In the context of Heracles, the risk class provides an indicator of the probability of a certain CH element being damaged by the effects of a climate-related effect. As already clarified, a distinction is made between potential damage, or damage type, and actual damage. The system also records potential mitigation actions and actual performed actions. Models and observations. The knowledge base of the Heracles platform stores metadata about sensors, models, measurement campaigns, and observations in general. Metadata about time series are stored by using an adapted version of the SensorThings API data model. The metadata includes pointers that enable access to the actual data, which is managed by a SensorThings certified server. The SensorThings API data model has been extended and adapted to handle metadata about geospatial coverages, geospatial shapes, and other documents. The model provides a comprehensive solution for dealing with all means of data generation, sensors, measurement campaigns, and models, and all the types of data that the sensors and models produce, time series, geospatial shapes, coverages, and documents. An asset representation is an entity that provides data about an asset. It can be regarded as a proxy that enables access to the available data about an asset. For example, temperatures in a building, pictures and measurements of the building obtained in a measurement campaign, are the results from a structural model. The data is organized into data sets, and the actual values are available in repositories outside the knowledge base. For instance, SensorThings API server, a server implementing protocols like WMS and WFS, or a repository providing access to documents. The four classes on the left in the figure, task and capability, task, input parameter, and parameter value, provide support to store and manage metadata about the models. Stored knowledge. The knowledge is structured with formal naming and definitions regarding data types and the interrelationships of entities. The ontology contains 110 classes, 165 object properties, and 48 data type properties. Heracles is a complex project with end users from diverse background and heterogenic needs. Therefore, the knowledge stored in the KB comes from several domains. The colored areas in the diagram symbolize the whole knowledge in the knowledge base. It consists of knowledge from several domains, the outer circles. Through synergy effects, the whole knowledge is greater than the sum of its parts. Platform architecture is the 7th chapter and is organized into a number of subchapters. The first 7 are platform users, integrated dashboard, CAP mobile app, Workflow Engine, CAP Web App, ECM Alfresco, and Data Fusion. Platform Components Diagram. The Heracles platform, developed under WP6 activities, is built by using already existing components that, if necessary, are improved or adapted for the project needs and additional newly developed components. In order to fulfill the end user's requirements and deliver the needed functionalities, all the different components were integrated in such a way that they can support common business processes and data sharing across the whole platform. The analyzed integration aspects deal with secure and reliable data exchange between the components, technological diversity including different communication protocols and messaging formats, and authentication and authorization matters. We created a platform that is based on both direct communication between components and a loosely coupled integration exploiting a common message broker solution whenever an asynchronous, event-driven communication mechanism is deemed necessary. The depicted diagram shows how the different components of the platform are grouped according to their main responsibilities, as described in the architecture specification. Presentation layer is in light blue, business layer is in red, data storage and sensing layer are in green, and infrastructure layer is in yellow. The table lists the main user roles recognized by the platform and the DSS functionalities accessible by each user role. Currently, we have configured 6 user roles: Site Manager, Domain Expert, Climate Change Expert, Risk Assessment Expert, On-Field User, and Administrator. The integrated dashboard is the main UI designed as a web application and enables the users to access the Heracles platform from desktop computers. The functionalities provided by the ID pertain to 2 macro blocks: situation awareness and decision support. The SA block comprises interactive visualization of the collected data and the derived results produced by algorithms and models. It also provides different granularity levels of visualization covering global and detailed views. The DS block comprises display of the generated alert based on COP messages. It supports the execution of the risk management workflow based on the related operational procedures. Moreover, the ID provides the access to other specific UIs implemented by other platform components, namely Knowledge Base, ECM Alfresco, CAP Web App, and Data Fusion. BibleRIA, a JavaScript data visualization framework from Thales, which supports a wide range of visualization types, 2D and 3D cartography, charts, 3D models, video, and timelines, was adopted for development of the Heracles ID. Thus, in the case of the Heracles platform, sensor data and 3D model visualizations are achieved by using BibleRIA. The Heracles Decision Support System is a presentation layer with an operator console for real-time signaling and intervention. The DSS processes and integrates heterogeneous data and is triggered by the right pattern of events in order to require the right human intervention when situations are critical. The integrated components, described in the following paragraphs and accessed through the menu bar of the DSS homepage displayed below, are sensors, which contain links to Frost IOSB and 2D, 3D GIS data, where users can access both using the DSS and a standard GIS client like QGIS. PS, permanent scatter, which contains links to 2D data, where users can interact with satellite measurements of displacement and visualize the temporal evolution over wide areas with millimetric precision. KB, with links to the knowledge base, where users can view Heracles use cases, data, metadata, as well as relationships among data from different sources based on the Heracles ontology. CAP, links to the CAP web app, where users can send and manage messages compliant with the Common Alerting Protocol. CAP messages are routed by means of ActiveMQ, the message-oriented middleware used by Leonardo as the communication bus for the Heracles DSS. RM workflow links to actionable procedures, where site managers and domain experts can manage creation and drafting of expert reports. Documento, with links to Alfresco, the web content management component of the Alfresco communication editions, named Alfresco Share, where users can create and manage documents according to a Leonardo customized document submission and approval workflow, accompanying the RM workflow. In designing the Heracles platform HMI, we followed the module tab as the user interface design pattern, in order to keep logical contents separated into different panes, and each pane viewable one at a time. The user requests content to be displayed by clicking the content's corresponding tab control. Module tabs are seeing an increase of use as websites and web applications push for optimizing web page screen areas without sacrificing the amount of information presented all at once. For example, in weblogs, they are used in secondary content sections, such as the sidebar, to present relevant and interesting information, such as a listing of blog posts, which users can interact with to get to web pages quicker. This inevitably allows for an unobtrusive and compact manner of presenting content. The result of the module type design approach in Heracles is to allow users to view a group of related data one at a time, which in turn allows designers to modularize this group of information in a compact manner, saving valuable screen space. The COP mobile app enables on-field users, for instance site guards or in-situ team members, to have a remote access to the Heracles platform. It allows a bidirectional interaction with the platform. On one side, receiving COP messages generated in a platform through the COP web application, and on the other side, reporting from the field to the platform. Some workflows provide the COP message as an output object. The mobile app is integrated with the DSS through the use of a message bus, allowing reception of COP messages generated by the RM workflow or a COP platform tool. Since people in the field are not able to access the Heracles DSS, the mobile application is used to provide them the latest information in an easily consumable way. Workflow engine. This is the back-end component that enables the platform to implement and execute workflows, which are based on the OPs defined under WP7 activities. Currently, the risk management workflow is deployed. The implementation leverages the capabilities offered by Flowable, a lightweight business process engine written in Java. Flowable allows to deploy BPMN 2.0 process definitions, an industry XML standard for defining processes, creating process instances from process definitions, running queries, accessing active or historical process instances and related data. The BPMN process definition for the risk management workflow, first designed by WP7 experts, was imported in Flowable and further refined in order to be integrated within the Heracles platform. Flowable provides REST APIs for the management of the processes executed by the workflow engine based on Flowable. In particular, it provides services in order to get information about active tasks, UI form properties, process variables, and to command actions such as starting a new process or advancing an existing one by submitting a form or completing a task. The RM workflow of the workflow engine. This is the back-end component that enables the platform to implement and execute workflows which are based on the OPs defined under WP7 activities. The implementation leverages the capabilities offered by Flowable, a lightweight business process engine written in Java. The COP web application enables a platform user with the appropriate authorization to send alerting messages compliant to the COP standard whenever a threat is identified, evaluated as significant or deemed a false alarm. The Heracles COP web application implements a subset of the standards tailored to the context of cultural heritage. In other words, the contents of the COP message have been aligned to the concepts described in the Heracles knowledge base ontology. The component provides a UI that is integrated into the ID through a dedicated tab. The risk management workflow requires the site manager to use this tool in the following situation. A threat has been identified that can be a climate-related event, for example, a flood or landslide, or a damage that has affected a cultural heritage site, for example, material degradation, erosion, cracks. In this case, the site manager is requested to create and to send a COP message to signal a threat. Another situation is the previous threat hazard has been quantified and evaluated as significant. In this case, the site manager is requested to create and send a COP message to update the situation. ECM Alfresco. Alfresco is an enterprise content management system chosen as the document management tool for the Heracles platform. In order to manage the entire life cycle of the reports provided by the domain experts during the risk management workflow. The Heracles risk management workflow requests that users, domain expert, climate change expert, risk management expert, create a report document and then send it to a site manager who can approve or request further integrations, corrections to the expert, thus implementing a cycle of report drafting, submission for approval, review, and requests for further corrections until final approval. Leonardo chooses the combination edition named Alfresco Share, a free LGPL version 3 licensed open source software version of Alfresco. Alfresco provides a UI that is integrated into the ID through a dedicated tab. The data fusion component is the semantic information fusion service that provides the synthetic descriptions of several pieces of information that a user wants to combine and aggregate. It enables the provision of a synthetic view of a subject and the query of this view for specific subviews. The following functionalities are provided by the information fusion service. Information synthesis. The information synthesis enables one to collect and organize information about a specific subject. Through information synthesis, all the gathered information items are organized into a network. The redundant part of the information items is detected and eliminated. For instance, input, domain ontology, similarity fusion operators table, list of information items to be aggregated. Output, an information network, in JSON format or customized text file. Another service is the information query. All the instances of information corresponding to a specific pattern query may be found within a network of information through the information query function. The input is always the domain ontology, similarity fusion operators table, information network, and the output is a list of information items matching the query in JSON format. The UI displays the result of the fusion of information regarding archaeological sites, either located in Heraclion or related to the same culture as the Palace of Knossos. The information related to the site, in our case the Knossos Palace, was acquired automatically from the Wikidata ontology and the Wikipedia encyclopedia after having using the data fusion service. The UI depicts a non-redundant and complete network of information available for the site, given the sources that were provided to the data fusion component. In the example in the figure, information about Knossos Palace, as well as its geographical location and other historical sites from the same period, were automatically retrieved and aggregated in an information network. Any information that was redundant from one source to another was removed, and any information from one source that could be refined thanks to another source is depicted in its most refined version. Given this network of information, the data fusion service may then be used to query the information for many purposes. For tourism purposes, for instance, one may query the information network for information about sites that are similar to the palace. Similarity may be viewed from different perspectives. Tourists may be interested in sites in the same geographical area or in sites from the same period, or even other types of sites, museums, etc., from a specific period or in a specific geographical area. The remaining 4 subchapters of the Platform Architecture chapter are Knowledge Base, Frost Server, GeoServer, and Infrastructure Components. We will now illustrate the 4 components colored in green in the Platform Components diagram. The Knowledge Base provides a consistent view of all data available inside the platform, structured through the Heracles ontology developed under WP5 activities. The KB stores current information about metadata such as the history of the monitored CH asset, current damages, possible risks, used materials, sensors, workflows, and so forth. Additionally, it describes the relations between the ontology and the entities stored inside other platform components. For example, data of the Frost server, data of the GeoServer, workflow processes of the workflow engine. The KB is implemented by using the Web Genesis system developed by Fraunhofer ISB. Web Genesis is a content, community, and knowledge management system. It supports the user by providing several options for manipulating, requesting, inserting, and visualizing data. Unlike many other CMSs, it is also able to work with ontologies. The KB UI is integrated into the ID through a dedicated tab. Moreover, it exposes a SPRQL endpoint, allowing other components to retrieve the stored information. Other details can be found in deliverables 6.2 and 6.3. There are 3 figures here in this slide. The entry point of the Heracles ontology in the top left figure is used to navigate through an ontology. The user must have read access. The tree diagram on the left shows the concepts within the ontology. You can navigate the ontology by clicking an entry in this tree. You can also navigate through the ontology picture on the right by clicking on one of the elements inside. This picture can be customized and shows the user required relations. In the top right figure, you see the possibility to populate the ontology. Web Genesis offers the possibility to create an input form for a class of the ontology, and after to insert a new instance by filling the related form. In the bottom center figure, you see the possibility to request data from the ontology. It supports the user by offering a graphical query editor. In the Palace of Gubbio page, in this instance example, you can see a visualization of an instance. It shows a monitored cultural heritage site. The KB gives information about metadata, such as the history or the most recent usage of the monitored object. In addition, it offers information about hypothetical and existing relationships between the CHSs and, for example, current damages, possible risks, or used materials in the CH. The named objects, again, have further relationships to other objects in the knowledge base, creating a network of concrete data. The example considers the Palace of Gubbio instance and its relationships. The Frost server provides storage capability for time series sensor data as well as for time series based model results. The Frost server is an open source server implementation of the SensorThings API developed by Fraunhofer ISB. It is written in the Java programming language and can be deployed on an open source Tomcat application server. Internally, it uses a Postgres SQL database for data storage, with the PostGIS extension to support geospatial queries. Frost is available online. The things in the SensorThings API are representations of cultural heritage assets such as the Palace of Gubbio, or measuring stations near assets such as the weather stations in Iossos and Koules. Each thing has data streams containing the data from a single sensor that measures a time series for this thing. Each data stream has a collection of observations that contain the actual measurements from the sensors. Each observation contains the results of a measurement and the time when the measurement was made. SensorThings API defines a RESTful interface to access sensor data over HTTP in an on-demand fashion, with data encoded in the developer-friendly JSON format. It offers rich querying mechanisms to request relevant data based on, for example, location of the feature of interest, time, type of sensor, or observed property. The GeoServer delivers services for the management of geospatial data. In particular, it provides storing, querying, and visualization functionalities for the Heracles platform. The data sources managed by the component are detailed in Deliverable 2.1, Geomorphological and Structural Modeling and Monitoring, and in Deliverable 2.2, Climate Change, Extreme Weather Conditions, and Anthropogenic Pressure Modeling. Moreover, in order to provide a 3D visualization similar to a virtual environment, GeoServer also exposes a binary 3D decimated mesh of the sites to be integrated into the 3D viewer. GeoServer software is compliant with OGC standards and exposes the following interfaces: WMS, WMTS, WFS, WCS, and CSW. The infrastructure components are also listed in this slide: ActiveMQ, IAM, and SMTP server. ActiveMQ is an open source message broker, JMS 1.1 compliant, message-oriented middleware from the Apache Software Foundation. It provides high availability, performance, scalability, reliability, and security for enterprise messaging. ActiveMQ supports a publish-subscribe messaging model built around the concept of topics. Each message may be delivered to multiple consumers which are interested in a specific topic. The publish-subscribe pattern is used within the Heracles platform whenever a loosely coupled, asynchronous, event-driven communication mechanism is required. Specifically, two topics are configured on the broker: cap.event for cap message communications, from cap web app to ID and cap mobile app, and from cap mobile app to ID. Another topic is WF-info for the notification of new workflow tasks to be executed by a specific user, from workflow engine to ID. ActiveMQ supports multiple language clients such as Java, C, C++, C#, Ruby, Python, and more. It provides support for multiple transport protocols, where TCP is the most commonly used. Moreover, ActiveMQ supports multiple wire formats such as OpenWire, STOP, REST, MQTT, and more. The Identity and Access Management component manages user authentication and authorization in the Heracles platform, enabling centralized administration of user data and single sign-on capability. The IAM solution chosen in this case is Keycloak, an open-source implementation of OpenID Connect, one of the current state-of-the-art standards in this field. The SMTP server chosen is Postfix, a free and open-source mail transfer agent that routes and delivers electronic mail. The mail server delivers a FISCO to send email notification to the users involved in the documental management workflow. Chapter number 4, Platform Deployment. The Platform Deployment Diagram. For integration and demonstration purposes, an installation of the Heracles platform has been set up in a cloud infrastructure provided by Leonardo. The deployment diagram depicted in the figure describes the mapping of the software onto the hardware and shows the system's distributed aspects. The different components have been deployed at 2 VMs hosted by the Leonardo cloud infrastructure. A third VM has been set up in order to provide proxy, reverse proxy, and mail server functionalities. The only exception to the centralized deployment regards the GeoServer component, which is directly hosted by Ageos in order to limit the infrastructure's cost by leveraging the serving capabilities of Ageos. The administrative access to the network has been granted by VPN connection for all the development partners. For the CentOS VM, considering that it has been shared by two different Heracles partners, in other words, IOSB and Thales, a containerized environment based on Docker CE has been adopted for the deployment of the different components. This allows a reproducible deployment of software components to the integration environment and an isolated execution environment for each container. In other words, each component can have its own dependencies without the need to coordinate this with other components. In addition to the VPN connection available for integration and administration purposes, a public interface has been provided in order to expose the Heracles platform on the Internet. This allows the platform to be available to all the stakeholders involved in the demonstration and validation activities. The HA proxy component, acting as reverse proxy, first controls the routing of the upcoming requests at the public interface to the rect module on one of the two VMs, and secondly, provides a centralized implementation of network encryption, SSL termination. The public IP address of the Heracles platform host is 94.127.86.132, and the FQDN registered for it is dss.heracles-project.eu. The integrated dashboard, which is the platform front end for desktop users, has been made publicly available on the internet at https://dss.heracles-project.eu/ and requires a modern web browser such as Chrome 60+ or Firefox 60+ to be properly executed. A COP mobile app enables access to the platform for a user on the field and requires a mobile device running Android OS. Chapter 5, Platform Unique Features. For many years now, information and communication technologies have been offering an ever-increasing support to cultural heritage preservation and exploitation. At the beginning, the focus was on the cataloging of cultural heritage and related metadata, transferring paper cataloging cards into the corresponding digital metadata, and subsequently on the digitation of documents and multimedia objects such as photos and models. More recently, the development of ICT provides us with the possibility to enrich and augment the original preserved information in order to make it easier to retrieve and explore such information, thus allowing operators to fully leverage all the knowledge and expertise they have. The main features of the Heracles platform are the capability to integrate heterogeneous data from multiple sources, the capability to integrate data resulting from offline user execution of predictive models, supporting the user in analyzing the data collected in order to evaluate the state of CH assets and related risks. In addition, the possibility to exploit and preserve CH on the web and mobile devices, and interoperability. Regarding exploitation of CH on the web and mobile devices, this further relevant topic concerns special characteristics of CH exploitation preservation by combining web and mobile devices. Mobile devices are more pervasive than laptop and desktop computers. Thus, they must be considered as fundamental instruments for exploitation preservation. Combining the web and mobile devices can result in relevant improvements for the distribution and integration of digital contents, also for communication purposes, as we do with the COP app. A special field of interest for further development concerns the use of georeferenced information systems, for example, the integration of maps in browser and mobile applications. Another feature is interoperability. A key point for Heracles is certainly the interoperability of CH digital archives. Interoperability implies that the actors, site managers, domain experts, operators of different CH sites agree to join their contents so that users can navigate multiple archives as a simple, larger archive, and basically allow site managers to fully understand the severity of the CH condition and operate promptly according to well-defined and shared procedures. Heracles, a unique platform for management of data related to a CHS. What makes the Heracles platform unique? Acquisition, metadata and indexing, and that it is a digital platform. Acquisition. Heracles allows you to avoid to discriminate between information that can be dematerialized, for example, temperature time series, and information that cannot, either for physical reasons, for example, 3D objects, or logical reasons, for example, intangible information such as workflows. Metadata and indexing. While a good solution for cataloging and digitation, both originating their own metadata, could be fully satisfactory for preservation purposes, additional information is provided by the Heracles platform to improve information retrieval of CH metadata and related digital objects within the KB. The key improvement in making this approach effective and economically viable is the automation of the discovery of additional information. This is the most relevant advance of Heracles platform in this direction, and is achieved by introducing relational data schema. Metadata tags coming from taxonomies built up during the cataloging process, multimedia tags coming from manual and/or automatic recognition and indexing of multimedia contents. Finally, it is a digital platform. Specific architectures for CH information systems must be considered to handle large CH archives, carefully distinguishing between preservation and exploitation needs. Generally, a CH metadata archive is not too large. Hypothetically, we can estimate the number of data bytes per archive in the order of the thousands per CH digital object. Subsequently, we could consider those metadata archives having several digital objects inside. In this latter case, the corresponding storage dimension would be of some terabytes approximately. Multimedia Heracles archives are even larger, at least 3 or 4 orders of magnitude more. They are really big data, since an ultra-high definition images, as well as 3D representations or points cloud, could be some terabytes large. CH digital archives requiring these space occupations are not uncommon. Similar considerations can be done for satellite images and multispectral data.